Hi everybody, welcome back. Today I thought I'm just going to give you an overview of the circuit for the controller card as it is drawn in the schematics to make the PCB. Last time we looked at the simulation model. It's basically the same circuit, just the ordering of some of the signals has been changed for convenience, but functionally it's the same circuit of last time. Regarding the question I asked last time, should I map the halting logic on a programmable chip like a PLA or a GAL, a GAL as they call it, and your feedback was in line with my own feelings, meaning that I should do that to preserve flexibility. But then when I started doing it, I realized that the cheap available PLAs that everybody can program with a TL866, that cheap little EEPROM programmer that can also program PLAs and PALs. What I could do with that, the chips that I could use with that programmer, was such that I couldn't use two different clock signals for different flip-flops in the chip, which I needed to, unless I would redesign the circuit. I didn't want to do that. So in the end, I decided not to use a PLA. I mapped the halting logic on standard 74 series logic because the 7474 allows me to use two completely different clocks for the two flip-flops in the chip, which is what I wanted to do. I do continue to use a PLA in the little circuits to identify a opcode corresponding to a load immediate instruction. And that PLA you can see even in the simulation circuit, it's all in the repository. So the PLA that you see in the simulation circuit, I am using in this circuit here, which is what is driving the design of the PCB. So let's review this. In the meantime, I resimulated things more. I thought about it more carefully again, and I think the circuits are correct. So I'm prepared to take the risk and go to hardware. And if it turns out I'm wrong, then hopefully I can bodge something later on and still use the board or make a new board. Yeah, it's a calculated risk. If I were working for a company, I wouldn't go to hardware before doing a top-level simulation of everything. But this is a hobby. I want to do what I find fun, and I don't find fun going through all the trouble of setting up a complete simulation of the whole thing. I don't want to bother with that. I'm a hardware guy. I like to touch tangible hardware. So I'm going to run the risk and go ahead with this. And I will be using this video as a sort of a final check, because since I set out now to explain to you everything I did, it works as a review for myself as well. It's a way to look at everything with fresh eyes, since I have to explain everything. All right, there are 6 sheets to the circuit. This is the first one. Then we have another one here, yet another, this, and then just the I/O part. So let's start from the beginning. This is the power supply circuit that you see here on the lower left. It's the same as in all the other cards, so there's nothing to explain here. It's all the same. This is just the power LED with the current limiting resistor. And as before, this card will work in 2 modes. One as a standalone mode, where the signals are driven by dip switches, or a in-system mode where all the signals come from the backplane. In the case of the standalone mode, we need 2 buttons for reset and clock, because they will be manual now, plus a little debouncing circuit. This is identical as to the previous cards as well. So it's all the same. I'm not going to explain this further. And then in this part here in the middle, we have the selection of whether the signals come from the backplane or come from dip switches. These 2 first bus drivers here drive the signals if they come from the backplane. So we have the system clock that comes from the backplane, the reset, the halt, the clear outgoing mail flag, and the set incoming mail flag signals. And then we have the 8 lines that come from the instruction memory It's basically the data bus of the instruction memory. I call it op-IMM, which is opcode or immediate, because both opcodes and immediates can come from the instruction memory. So all of this comes from the backplane on this side, and then on this side it's the same signals, but instead of coming from the backplane, the first two come here from the little push buttons that do the reset and clock, or they come from dip switches that you see here, which allow the user to set the signals at will when the board is used in standalone mode. Of course, these two switches are dip switches, so you need to pull their values. In this case, I'm pulling the values up. So if the switch is not connected, then we get 5 volts. If the switch if they are not connected, then we get ground, because they're pulled down, not up. I'm sorry, they are pulled down. And if the switches are connected, then we get 5 volts or VCC. Here on the other side, the signals are merged together, so we get these local signals: local negative reset, local negative halt, local clear outgoing mail flag, local set incoming mail flag, and then the op-IMMs, and they will either be from the switches or they will be from the backplane, depending on how we set things via this signal here, which is backplane output enable or switch output enable. All right, now for these control signals here on top, they also include the clock, which you see here. That's the system clock that comes from the oscillator. We have another driver that drives an LED bar through a resistor bank of 1 kilo ohm resistors to limit the current that comes out from the transceiver, so we don't wear off the transceiver over time. The same thing here on this side. This corresponds to the op-IMM signals, as you see here. They come out and they are labeled here, they go down, and then they go through a buffer again, 1 kilo ohm resistors, and then they are displayed. So DS2 or display 2 shows what's coming out of the instruction memory, which is either an opcode or an immediate, and display 1 over here will display the values of these control signals that again will either come from the backplane or from switches. Now this circuit that you see here in the middle, here you see in red, that's what deals with the mail flags, the outgoing mail flag and the incoming mail flag, because they can be set or cleared either from within the CPU itself. There are instructions for it, as you can see in the instruction set architecture spreadsheet in the repository under the director ISA, or they can be set and cleared from a DMA device outside the CPU. So this is the logic to handle that over here. And this inverter is also used to generate the negative system clock, which is out of phase with the system clock by 180 degrees. It's just a negated version of the system clock. We need both. All right, let's go to the next sheet. I call it halt because the halt logic is in here, but there is more to this sheet. For instance, this bottom part here, in here, it's part of the logic to select signals from a switch or from the backplane. Namely, it's about the 6 flags that come from the ALU. If they come from the backplane, then this buffer is active and this one is tri-stated. But they can also come from another dip switch with the pull-down resistor network, in the case that you're using the board in standalone mode, and then the user has to set the dip switches to emulate the flags coming from the ALU. So when they are set by the switches, then this transceiver is active and this one is tri-stated. And then we get the local flags here on the other side. And these same values, as you can see here, they are also displayed in another LED bar, DS3. Again, driven by a dedicated buffer just for that, 1 kilo ohm resistor array or resistor pack, whatever you want to call it, and the LED bar itself. All right, now this is the logic that when what's coming from the instruction memory is a load immediate instruction, then it sets things up such that in the next cycle the processor will fetch a no op, because the next content from the instruction memory will be an immediate value. So on the opcode path we have to put a no op, and this is the circuitry that does that. We talked about it in the previous episode using the simulator. This is the PLA. It keeps spying the 8-bit value, or the byte that comes from instruction memory, to detect a load immediate, which is an opcode of 1, 2, 3, 4, 5, or 6. And if it is, then this line here on the output will be a 1, and that goes into the logic. And out of the logic comes this signal, the NOP output enable, which is active load. That's why the N, or negated. And that will tri-state a buffer that passes on the opcode value, and therefore the opcode value will be pulled down. We discussed all this last time, and it will be a no op, because no op is opcode 00. So this is this part here. And then we have the halt logic over here, which we discussed last time as well. And as I told you, I'm going to use two 74 logic ICs as opposed to a programmable PAL or a PLA or a GAL, because I can use two different clocks for the two different flip-flops entailed by this chip, the 7474. And you can see it already here. Let me see. I can use either the negated system clock or the system clock, depending on the flip-flop I am using, and that's what I wanted to do. And then there is this other chip here with a couple of logic gates. That's a 7408. I added one extra buffer, a 74244, because the clock signals, the negative clock and the clock, especially the clock, the negative clock stays on this card, but the clock goes to all the other 4 cards via the backplane. So I wanted it to be driven with some oomph, and not driven just from the output of a logic gate. So that's why I put a 244 in there to give it some more oomph. Again, a 33 ohm resistor just on the driver side to eliminate the reflections from the higher frequency harmonics. And then since I had this 244 there, I also buffered the N clock and the program counter output enable, which also goes to another card, namely the addressing logic card. So this is it for this page. Now let's go to the decoding part. That's when everything we've seen so far is just control and fetch. And now we go to the decoding stage. This is the NOP generator that I mentioned before. This is the key control signal, the NOP output enable, and as I discussed, it's generated here by this logic. And the reason is, when the previous opcode was a load immediate, then this transceiver will be tri-stated for the next content coming from instruction memory, and therefore this resistor network here, which pulls everybody down, will dominate, because the transceiver will be tri-stated, and the value that this chip will get, and this is the instruction register, will be a 0. It will get a 0. In other words, a no op. So it will always get a no op immediately after a load immediate opcode, because the next content of instruction memory would then be the immediate value and not an opcode. So what does the IR get? It gets a no op. We discussed this previous time. And then the contents of the instruction register are visualized here. So there is a buffer dedicated to driving LED bar through current limiting 1 kilo ohm resistor pack. All right. Now, these 4 memories here, they are the decoding memories we talked about last time. They will receive the contents of the instruction register as input, and the output will be the 31 values of the control lines that go to all 4 CPU cards. Now, I've decided to use flash memory. I'm using here an SST39SF020. These are just flash memories from microchip. They are deep packaged, duo inline package. So they will look like the other ICs, just a little bit bigger. There are 3 versions of them with different amounts of memory. I think one is 128K, the other one is 256, and there is one with 512 kilobytes. They all have the exact same footprint, so they all fit in the same socket. But depending on the version, some of the address bits are not used. For instance, address line 18 and 17 are not available in the 128K version of this flash memory. It's a non-connected. Because I wanted to keep flexibility to let people use any of the 3 variants of these chips, I added a little, logic here on top. Includes this as well, and this, which allows you to set some of the higher address lines, like address line 18, 17, and 16, using shunts on pin headers, because Talos uses only 64 kilobytes. So if you're using, say, 512 kilobyte memory, then you can select which segment of that memory will actually be used by Talos by setting shunts on these 3 pin headers here. And that in turn would allow you to have pre-programmed multiple different versions of the Talos instruction set in different regions of the flash memory, and then selecting which instruction set you want just by putting a shunt on the appropriate pin headers, or removing the shunt from the appropriate pin headers. That's the idea. In principle, what you see here in this part here are just the 4 decoding memories with these pin headers to allow you to set the higher order address bits. And then the output from the decoding memories go into the decoded instruction registers, or DIRs. Just like we saw before, I'm using 74273 chips with 8 D flip-flops. This is just like we've discussed last time. And the outputs of these decoded instruction registers, I'm numbering them, I'm calling them DIR for decoded instruction register, and then a number to identify which bit it is. So you will see these DIR signals elsewhere. They go from 0 to 31, because there are 32 bits. One of them is free, but I'm still labeling it. Now we are in the execute stage of the pipeline. If you notice vertically, there are 4 identical vertical circuits. They are not nicely aligned horizontally, because otherwise they wouldn't fit in the space. So I sort of shifted them vertically up and down so I could fit everything. But they are essentially identical circuits. It's what I marked here in red is one of them, one of the 4. But of course, they take signals from different ones of the decoded instruction registers. So this takes bits 24 to 31. This one takes bits 16 to 23. This one 8 to 15, and this one 0 to 7. So you deal with all 32 of them. And the outputs that come from instruction memory are buffered here. So the outputs are these. So they are buffered to strengthen the signal. They are pulled down by this resistor network. Because, for instance, if Talos is in a halt mode, then this control line here, the decoded instruction register output enable, will be inactive, which means that this buffer will tri-state, and this resistor network will pull every signal down. These signals will be 0, and therefore all the other buffers and transceivers in the CPU will tri-state as well. And that's what you want when you are in a halt state. You want all the address buffers, all the address buses, data buses to be tri-stated, so an I/O controller, a DMA device, can take control of the buses. So that's what's happening here. And then again, whatever is coming out of this buffer, which may be pulled down by this resistor network, is visualized by this little circuit, which is just yet another buffer, because you don't want to drive LEDs with lines that have a logical value. You may screw up your logic if you do that. So there is an extra buffer just to drive the LEDs, current limiting resistor pack, and the LED bar. And you see the same thing all 4 times. And finally, that's the part of the logic that deals with the immediate value. This is the immediate register that will receive a byte from the instruction memory, while the opcode will be a NOP, a no-op. Now, the contents of the immediate register are then buffered again, and they can go either to the internal bus high or to the internal bus low, depending on how you set the control lines, which are here and here. And the control lines are determined here. I will talk about it in a moment. Every bus in an architecture should be pulled down or pulled up. In the case of the external buses, I will pull them up or down. I'll pull them up on the backplane board. But in the case of the internal buses of the CPU, I haven't pulled them up or down anywhere else. So this is the time and the place to pull them high. I'm pulling them up over here to give them even a little more oomph after the buffer. So if the buses are left undefined, then the contents will be high. It will be FF. That's the idea. You want to have the buses always either defined or explicitly tri-stated, so a DMA device can take over. But if a DMA device is not taking over and nobody else is driving the bus because you have, I don't know, an ALU instruction, for instance, not a register to register instruction, you want to pull them either high or low. I prefer to pull them high. So they are not left undefined ever. And the contents of the immediate register are visualized here. Again, dedicated buffer, current limiting resistor pack, and LED bar. Now, the control lines that go into these 2 buffers, deciding whether the contents of the immediate register go into the internal bus high or the internal bus low, they come from this little NAND gate. And the control lines actually come from the decoded instruction registers. Immediate high output enable, immediate low output enable. If you go back to the execution stage, actually to the decode stage, where is it? Here. Where are they? Here they are. So they come from the decoding memory 0, the first one, and they come out here, and from here they come in here, and then they go through both inputs of NAND gates, so they're basically inverted. And we need to invert them because the output enable lines of these 2 chips are active low, but the logic of the CPU is the opposite. It's positive logic, so we need to invert them. And again, why am I using positive logic? Well, because if I reset the device, I want everything to be tri-stated and the values to be 0 since they are being pulled low. So I use positive logic, but here I have to translate them into negative logic for these 2 buffer chips. The same NAND gate is used to both invert the read, which is active high, but when it goes to memories, to outside memories, the read strobe of outside memories are almost invariably active low, so it needs to be inverted. I also put a 33 ohm resistor there to cut out the higher harmonic reflections, and a pull up. Everything should be pulled up or down, including the control signals. And the final NAND gate is used to end the write strobe with the clock, for reasons we discussed in previous episodes, and invert it at the end. That's why it's a NAND gate. And again, a little 33 ohm in series resistor and a pull-up. So that's basically it. In the final sheet, we have the decoupling capacitors of 100 microfarad. And then we have the bypass capacitors, one for each IC. And these are the backplane connectors and the signals that go in and out. And this pretty much sort of complete the connections of the backplane. You see this non-connected here because these are ALU signals. They are the contents of A high, B high, A low, and B low that go between register file and ALU. So they are not connected here because this specific board doesn't use those signals. But this bit here with the green arrow over here, this 4 here and this 4 here, they are really not used by Talos. So they are really free. And for the system clock, you may notice that I surrounded system clock with grounded pins, and that's to prevent interference, to improve signal integrity, because the clock is the clocks. There are several clocks in Argon, but the clocks are the ones that if they get reflections, if they get poor signal integrity, you may get a false clock transition that screws really everything up, and it's the line that is switching most often as well. All the other lines do not switch every clock cycle, but the clock does switch every clock cycle. So it's even more vulnerable to reflections because of that. So I protect the clock lines more than everything else. And you will see the same idea when I show you the physical design of the board, which I will show you now. Here it is. That's the top layer. It's a 4-layer board. I didn't even try to do it in 2 layers because there are too many lines here, and this is the control board. So you really want every control signal to be clean here. You want to have proper power for every chip. You don't want to mess up with signal integrity anywhere, but particularly in this board, you don't want that. So 4 layers. We have the top layer and the bottom layer, which are signal layers. And then there is an inner layer 1, which is ground. It's a ground plane. And inner layer 2, which is a VCC plane. And the top layer has VCC copper fill, and the bottom layer has ground copper fill. So the idea is that you have VCC ground. You're how do you say? You go from VCC to ground, and then from ground to VCC as you go down the layer stack. That creates a capacitive effect, like the whole board becomes one large bypass capacitor, which improves the electrical performance of the circuit. What I'm going to do now, I'm going to hide the copper areas. I'm going to hide the top silk screen because I want to show you the signal layers. I'm going to go to blue because you can still see the red when the blue is active, but if I activate the red, then the blue almost disappears. So I will use this here. You may notice that I use that rule of thumb that you have a sort of preferential direction in different layers. So on the bottom layer, the preferential direction is horizontal, and in the top layer, the preferential direction is vertical. This is not because it looks cute. This is because it makes routing a lot easier. It prevents you from sort of locking yourself up in a jail of lines around it and preventing you from routing a signal. I'm consequential with this, but not blind. So in places where I would, in principle, have to use a via to change preferential directions. If I don't need to do that, then I don't. Let me show you some examples of this. For instance, here, this band here, in principle, you would say I should come with this line until here and then change layers and go up in red because red is vertical. But there was nothing else going on here, so why will I add an extra via for nothing? Just worsen the impedance mismatch of my trace. So I'm not blind. Here's the same thing. There are other places here. See this slanted line here is largely vertical as much as it is horizontal, but I'm not changing layers here. And this 4 over here, they also go slanted in red. I'm not changing to blue to cover the horizontal direction. And sometimes I even keep the same color for an entire trace. For instance, this trace here is largely vertical, it's mostly vertical, but I'm doing it entirely in blue. And the reason is, well, the trace density on this part of the circuit is low. So why will I blindly follow the preferential direction if I can avoid vias by keeping everything blue? So that's what I did. So you have to know the rule of thumb, which is preferential directions, and be consequent with that. But you also have to know when you don't really need to blindly follow the rule of thumb. That's the idea here. I try to keep the traces as far apart as possible. There are some areas of a little bit of congestion, like here, but if you zoom in, you see that the distance between two adjacent traces is about twice the thickness of the trace itself. So this is still a pretty good distance, and that's as bad as it gets. It's this area here. There is some congestion over here, here, and here. But in all cases, what seems to be a congestion from a relative perspective, if you zoom in, you see that the traces are still fairly far apart. And you want the traces to be as far apart as possible, because longer distance means that the traces can interfere less with one another. The field fringes of their respective electromagnetic fields, particularly the magnetic field, because if you have a trace that's going up and the current is flowing like this, then there is a magnetic field that wraps around the trace, like this. And because it wraps around the trace like this, if there is another trace over here, then this wrapping around sort of touches the neighboring trace, causing an interference. And you reduce that by keeping the traces as far apart as possible. Again, I see a lot of hobbyists that seem to think it's super cool and professional looking to tightly pack the traces as close together as possible. That's not it. You only do that if you have severe economic constraints on the size of your board, and you can only fit everything in if you keep the traces very close together. But short of that, if you have the space, you don't want to keep the traces very close to one another, sideways. What you do want is to keep the traces short. And that's the reason, for instance, why I'm not using any of this area here. Because you might say, well, if you have the space, why don't you spread things out more so the traces can even be even further away from each other? Well, it's because you have to balance that with the need to keep the traces short. The longer the traces, the more losses, the higher the signal propagation delay, the more the chance for interference, EMI, electromagnetic interference, and therefore poorer signal integrity, the higher the chance for reflections. The longer the trace, the lower frequency harmonics actually reflect on that trace. The longer the trace, the lower the frequency of the harmonics that can get reflected on that trace. In other words, you get more reflections if you have longer traces. So you have to balance things out. Sideways, you want the traces far apart from one another, but in length, you want them short as possible. And to give you a rough outline, let me show everything again and go to the top layer. These are the four instruction decoding memories that you see here. These are the four decoded instruction registers, or DIRs. They are here. Then they are buffered by the 74245 4 times. These buffers drive the lines that go to the other CPU cards connected to the same backplane. The buffered signal goes through 33 ohm resistor networks, this, and this, to reduce reflections, because these lines will go to the backplane where there is a big impedance mismatch because of the backplane connector. So there will be reflections, and you want to absorb them in this 33 ohm resistor packs in here. The final of the four does not have the 33 ohm resistor pack, because these control signals are used on this board. They don't go through the backplane. Only two of them go, and then I use two discrete 33 ohm resistors here The rest stays on this board, so we don't really need to pass everything through 33 ohm. They are not going to face the impedance mismatch of the backplane connector. For things that are on the same board, I only use 33 ohm resistors for the clock signal. So this is one of them. There is a clock coming out of this resistor here. Let me try to show you that it's not highlighting. This is the system clock. It's not highlighting it. So to highlight it, let me hide the copper area. Oh yeah, here it is. This is the line. This is the system clock line. So in fact, I can show you more. I can show you all the lines. What you want ideally is that every line is a snake. It goes from A to B, from B to C, from C to D, and never from A to B and from A to C. You don't want a split or a sideways path like that, because that increases reflections. Often it's possible to route everything such that you don't have this branching out. So every line is a snake. No line is a crab with branches, or a tree with branches. But this board was complex enough that I couldn't avoid one or two branches now and then. Let's look at some lines. What line is this? This is the decoding instruction register output enable. So it's produced by the logic on top and then goes down to the 4 buffers that drive out the decoding instruction from the decoding instruction registers. This one here, you see, has one branch. This one has one branch. If you look at the white, you see that there is one branch. It's at the very end here. So this is the line. This going to the right here, that's a branch. Ideally, I should have routed this line on top there and not down. But yeah, that was not possible. There is only so far. Well, actually, it would have been possible if I moved this line, but I didn't bother. It was a short branch, and this thing is not going to run at 10 megahertz. Probably not. Probably not. I'm thinking of 1 megahertz. I'm thinking about this design with 1 megahertz in mind, which gives me 1 microsecond per clock cycle. That's what I'm thinking about, and then that little branch wouldn't matter. There is another thing to show, and for this I have to show the copper area again. You will notice that in some lines I really shield them. For instance, this line, you see there is this vias surrounding the line all the way down. Why? What line is this? This is the clock line that goes to the other CPU cards. It's the managed clock. So it's one of the lines that's most sensitive, because it's switching all the time, more frequently than every other line. The clock always switches, since it governs the switching times of everything else. And this one will go through 4 backplane connectors, so we really don't want to compromise signal integrity already from the get-go, because signal integrity will be inevitably compromised later because of the impedance mismatches of the backplane connectors. So you want to keep this line as clean as possible. In every situation we can keep it as clean, that we can keep it clean. And one way to do that is to electromagnetically shield it, and I do that with the copper fill, which is VCC, and these vias, they are VCC, you see? And the idea is to stitch the VCC copper fill that surrounds the clock line on both sides, such that the copper fill is always at VCC for every frequency, even the highest frequency harmonics. You know, if I run this thing at 1 megahertz, we can have frequency harmonics at 20, 25 megahertz, depending on the rise and fall time of the clock signal. And so that's no longer a frequency that you can ignore. And at high frequencies, if you don't stitch the copper fill in every short distance, if you don't do that, effectively the copper fill may float for higher frequencies. So that's why I'm stitching the copper fill around the clock line every couple of centimeters, And not only that, sometimes instead of stitching the copper fill, I add a ground via. Like this is also a clock line. Let's see what line this is. This is the negated clock. And you will see that sometimes I put a ground via, which is not part of the copper fill of the top layer. It's part of the copper fill of the bottom layer. But I put ground here instead of filling this with copper, because I want to provide a current return path via for this pad. Now, is this really necessary? Not really, because the return current for a pad that's connected directly to a chip will probably run through inside the die. It will probably run inside the chip. But to make sure, absolutely sure, that I have no interference from this pad to the clock line, which runs right next to it, I put a ground via here. You can see this ground via as a sort of a lightning rod. That's one way to visualize it. You put a lightning rod, so whatever electromagnetic interference is coming from this leg, from this pin, it gets caught by this via, instead of the fringes extending and hitting the clock line. That's the idea. Now, when the via is VCC, it still works as a lightning rod, but the main reason to do that is to stitch the copper fill every couple of centimeters. All right, that's about it. I think that's all I wanted to talk about. These are the buttons for clock and reset. This is the header to decide whether you're using the boarding system or as a standalone board that you can test with your hands. I tried to make the silkscreen as visual and clear and explicit as possible. So these are the displays that visualize the control signals that go to the other CPU cards. And I put on the silkscreen here, I put the names of the respective signals that you see on each LED of this LED bar. So you know what's active, what is inactive. I did the same here for the control, for the flags coming from the ALU. I marked them. I use coarser grained silkscreen marking when we have, for instance, this switch S2 allows the user to set what would normally come out from the instruction memory, the opcode or the immediate. And then I mark clearly that this switch is about setting the opcode immediate value in standalone mode when you're not connected to an external instruction memory. In this case here, I describe explicitly what each signal is that you set on this other switch. Here I have this is yet another switch which allows you to set the ALU flags in standalone mode when you're not connected to the actual ALU, so they are all described in there. These are the headers that allow you to set the higher order address bits of the memories to allow you to use larger memories than Talos needs. And then I specify which memory and which address line it is, like this is decoding memory 0, address line 16. This is address line 17 here, 18 there. The same thing for decoding memory 1, address line 17, and so on and so forth. And over here, I explicitly mark the immediate value coming from the immediate register. That's what is displayed on this LED bar 9. And here we have another 2 LED bars, and this one shows the op-IM value, which normally comes from the instruction memory but can be set locally on this board when you're using it in standalone mode. And these one are the contents of the IR register. So I don't mark them one by one because this is just an 8-bit value starting from bit 0 and going to bit 7. So I don't need to mark each one of them. I just say this is the IR. These are the contents of the IR. I try to mark every chip with what chip it's using. I couldn't do it outside the socket everywhere. So here I put it outside the socket, so you still see it even if the chip is placed in the socket. But here I put it inside the socket, which is not very visible, but I didn't really have the space. For this one I had the space, but for this I didn't, because there is already a resistor network here, and there isn't space on top either. So my convention was the following. For the 245s, I put the silkscreen marking inside the socket, because most chips in Talos are 245s, the most useful chip. Tri-statable bus transceivers are the most usable chips, because you effectively build multiplexers with them. You tri-state one and you activate the other, or the other way around. That's a multiplexer that you do without logic gates, just with buffers, and they strengthen the signal at the same time. So most chips are this 245. So what you get is, when the board is populated, for the chips that you don't see any silk screen, it means that they are 245, because the silk screen is underneath the chip. For the chips that you do see the silk screen, they are not 245s. They will be 273s or 7474 or 08s or 14s or 32s or 14 here again, over here. So that's the idea. What else am I missing? I think I've discussed everything. So this is ready to go to manufacturing. There is one thing I did. This is the PLA. That's the socket where the PLA will come in. I can actually go to the 3D mode. Again, I don't bother loading the 3D models for every part. So the 3D model, the 3D view you're about to see is not complete. I just don't bother it. If I was fitting it to a small case, then I would load all the 3D models to see how everything is behaving. But here I didn't bother. And this is the PLA socket over here. The PLA will come over here. And I did already program the PLA and tested it. Let me show you that process. So this is the little PLA. I actually already programmed it, but I'll go through the steps with you, just in case you're curious. I program it on this Super Pro. This is a professional programmer, but you can use a normal TL866. This is how I designed the circuit in it. I used this tool, WinCouple, from Microchip. This is just the header and some properties that you define, and you declare the input and output pins. And the logic is actually this. There is only one output, PLA out, and it contains 6 product terms. Each product term is a big AND, and then ORed. This hash is an OR, the upper is an AND, and the exclamation mark is an inverter, is an inversion. So it's basically saying PLA out is 1 if input 7 is 0, 6 is 0, 5 is 0, 4 is 0, 3 is 0, 2 is 0, 1 is 0, and input 0 is 1 because it's not inverted. And then so meaning opcode 1, and then OR, and then another product term for opcode 2, in which input 1 is non-zero. And then you do the same thing for 3, 4, 5, and 6. In other words, if the input opcode is 1, 2, 3, 4, 5, or 6, then the output is 1. The output PLA out is 1. And you can just compile this. Compilation successful. That will create a JED file here, talospla.jed. And then with the PLA in your programmer, and you choose the device as an ATF16V8C, that's the PLA I'm using. You can just load the buffer here. So we just load that Talos PLA.jed. So the buffer is loaded with it now. Because I already programmed the PLA, we can just verify now. And verification is okay. You can do it again, the programmer will work. So this is how you do it. And then once you're through, you can just close this. You take your programmed chip out. And then to test it, I will use this little circuit with an LED on the output. And then I can just change the inputs from 0 to 1 or grounds to 5 volts and see if it's working correctly. So the PLA is now in there. These are the inputs. The output is here. It goes through this 1K ohm resistor and will light up or not the LED depending on where the inputs form a 1, 2, 3, 4, 5 or 6. Anything else the LED should not light. I'm powering it with my lab bench set for 5 volts and limited to 100 milliamps, which should be more than enough. So let's turn it on now. It settles at 67 milliamps. So this is now working. The input is all zeros, they are all grounded. So the LED is not lit. So if we go to input 1, now the LED lights go back to 0 and go to input, let's do input 2. At input 2, the LED lights. Input 3, it should light as well. Up to 6, it should light. So let's go back to 0 and do input 4. Oops. 4, it lights. And 6, it lights. But if I take the higher order bit and make it 1, then it doesn't light. And of course, I already did this for all the relevant combinations, and the chip is working fine. So yeah, the PLA is tested. I didn't bother test loading the 4 decoding memories that you see here. Those are the 4 flash memories. Because, yeah, okay, I know it works. And I didn't prepare the file that I have to load into them, because so far I have been doing all the simulations using one address per instruction, and I can do that if I ignored all the flags, all the 8 flags. But in the real board, I cannot ignore the 8 flags. So every instruction will occupy 256 addresses to account for the possible values of the 8 flags. And I'm not sure yet how to do that in PowerPoint, or I probably will have to write a Python script, because 256 instructions times 256 addresses per instruction is a lot of stuff to do manually. I didn't do it yet, so I didn't load these memories, but I know I'll figure out how to create the file to load in them as the board is being manufactured in China over the next couple of weeks. That's why I didn't try it. But these I already tried just to make sure, as you just saw. So when I get the board back, I will test it in standalone mode, doing the same things I did when we simulated the system, the same kinds of tests. And if everything's okay, then probably before I go to the real backplane board, which will contain all the system memories, will contain the I/O controller, will contain the serial interface that will connect to a terminal. Before I do that full time, I think I will build a simpler backplane board with a manually driven clock or a slow clock driven by a 555, just to test the whole thing together, to test the CPU together, not the rest of the computer, just the CPU, to see if all the signals are flowing correctly, if all the logic is working fine, if it's halting properly, if it's jumping properly. So I think I would do that first. It's an expensive thing because it will have to be a full-sized board. I will not explain why it has to be a full-sized board yet, because otherwise I would spoil a surprise. I want to show you what the backplane board will look like once I have a backplane board, even if it's not a complete one, even if it's just one that is playing the role of driver and stub to test the system. Even then, that will have the final format, and I don't want to spoil the surprise. I want to show that to you already ready, so you see the effect before I tell you what I have in mind to do that. All right, this is it. So this is what's going to the manufacturers, to PCBWay in China. And I'll keep you up to date. I think the next episode will be only next year, because I don't think I mean, I'm recording this on the 10th of December. No, it may be back just before Christmas. It may very well be back just before Christmas. If it is, then there will be another episode between Christmas and New Year. Otherwise, I wish you guys all, guys and girls, I wish you all a Merry Christmas and a fulfilling New Year. Let's hope 2023 has less conflict, less war, less catastrophe and death than 2022 has had. All right, take care, and I'll see you then.